Hello, students, and welcome to our lesson on solving word problems or practical application problems using trigonometric functions, and in particular, sinusoidal curves. So I have a problem here which states Emily rides a Ferris wheel. The wheel has a 16-meter diameter, turns at 3 revolutions per minute, with its lowest point 1 meter above the ground. Assume that Emily's height h above the ground is a sinusoidal function of time t, where t equals 0 represents the lowest point on the wheel, and t is measured in seconds. And we are asked to do two things. First, write an equation for h in terms of t, and then answer the question 33 seconds after the wheel starts, how far above the ground is Emily? Okay, and so there's a lot of things going on in this problem. So it probably helps just to look at an illustration of what's happening here. And you can see here in from my GeoGebra setup here that that Emily is here. It's a little bit cluttered there, but you can see Emily is here. Her name's written in magenta here at the start of this. The blue line here is the ground, and the circle here is the Ferris wheel. Okay? And let me just take away the XY coordinates here, just so that we can get a really good picture of what's actually happening here, and we don't have to worry so much about the graph just yet. Okay, and Emily is moving around this wheel, okay? And as you can see, as she moves around this wheel, we can look at how high off the ground she is. So she was just at 17, and now the wheel is sort of spinning around, and she's getting lower and lower to the ground. And then she returns right here, back at her starting point, and then she keeps on going. Okay, so you can see the height is ever changing, but it's changing in such a way that it gets higher and higher and higher. It reaches its maximum point and then comes back down. Okay? And we want to know that for any given time since she started moving, can we figure out how far she is off the ground? So let me just stop the animation there and sort of get back to our problem. And there's a lot of things going on here, so I'm going to start by drawing a picture. I'm going to move this down here, and I'm going to start by drawing a picture of what's happening. Okay. And so I have here is the wheel. Let me make it a better wheel here. It's pretty messed up Ferris wheel. I don't think I would want to ride that. Yes, that's better. Here is her. Here is the ground. Okay. And we know a few things. We know that it has a diameter of 16 meters, which means that it has a radius that's equal to 8. I'm not going to write radius. I'm going to write it over here. Radius is equal to 8. Okay. And we know that it's 1 meter off the ground. So then that means this distance right here is 1 meter. Okay. And, well, that's about all we know for now. One thing that I'm going to write here, it doesn't say how the wheel is rotating. It doesn't say whether it's counterclockwise or clockwise. So for right now, we are going to make a note here, and we're just going to assume counterclockwise rotation. Okay, since it doesn't say how it's rotating, so we're just going to assume that that's going counterclockwise. If you see a different problem and it says that you have to rotate in a certain direction, then you can't really make any assumptions. Okay. And our strategy here is a couple of different things. First, we're asked to find an equation of h in terms of t, which is time, but that might be a little bit too much to handle right now. So what I'm going to say here is write an equation for h in terms of theta, okay? And then we will convert theta to t later. Okay? And let's define what theta means. Since Emily is rotating counterclockwise by our assumption here, this is theta. Okay, so if she's rotating that much, we basically want to know how far off the ground is she. We want to know this distance as she goes around the circle. So I'll set this aside for now, and we're gonna work through this in a few steps. So we basically are looking for an equation in some sort of form like, f of theta is equal to something, and it's probably going to be a sinusoid. Okay, in fact, we were given that it's a sinusoid. So, it's going to be f of theta equals something. We need theta in here somewhere. But let's look at our strategy here, and let's go with the strategy where we compare the Ferris wheel to a unit circle. So let's say I draw a unit circle here, and it's kind of like a weird Ferris wheel that goes underground. And notice here that the radius of our unit circle is equal to 1, whereas the radius of our Ferris wheel is equal to 8. Okay, so the Ferris wheel is bigger than the unit circle. And a few more things that kind of jump out here. We have a center for the unit circle, okay, a center at 0, 0, whereas the center for the Ferris wheel, and we have to be a little bit careful here, it's 1 meters off the ground and then another 8 meters to get to the center because that's the radius. So the center here would be 0, 9. Because again, it's 1 meter off the ground and then another 8 meters to get up here. And let's look at a few more comparisons here before we really proceed. Notice here that for the unit circle Ferris wheel, we are rotating starting from standard position, whereas for Emily, we're starting from the bottom of the wheel. Okay? And so that's going to make a little bit of a difference. And I'll write this note in here that since Emily starts at the bottom of the wheel, she basically has a 270-degree head start. So if you imagine if, instead of starting here, she's already spun around 270 degrees or 3 pi radian compared to the unit circle. You can also say that she is, minus 90 degrees or she's 90 degrees behind. Both are saying the equivalent. Okay, so you can say that she, excuse me, she has a 3 pi over 2 radian head start compared to the unit circle. And that's going to be important as well. And really from this information, we can put together quite a bit here. Okay? So looking at our equation, the Ferris wheel has a radius that's 8 times bigger than that of the unit circle. So this is sort of like a stretch, of 8. And so we put 8 in front here of our sine function. And the other thing is that everything has been shifted up. So it's like taking our Ferris wheel and shifting it up 9 units. And we know that when you're moving something up and down for our function in terms of transformation, you're really adding to it. So we're adding 9 to it. And, again, instead of taking the sine of theta, well, we know that she has a 3 pi over 2 head start. So we have to add 3 pi over 2 to our angle. And you can see here that just from looking at this problem and comparing the Ferris wheel to the unit circle, we've gotten a lot done already. And we're done in terms of the equation using theta, okay? And we're actually pretty close to getting the right answer. And now before we said convert theta to t later, well, later is now. Okay? We've done as much as we can with theta. Now we want to convert it to t. And so we need some sort of information where we need to, compare theta over t. Okay? And keep in mind of our units, because this is really a unit conversion problem now. Well, theta is measured in radian, t is measured in seconds, okay? And so that's going to affect how things go. Now let's look at the problem again for one more bit of information. It says that it turns at 3 revolutions per minute. 3 revolutions per minute. So that means we have 3 revs per 1 minute, and we need to somehow convert it to radian per second. And this is a unit conversion problem. It's not too difficult to do. Well, you have 1 minute for every 60 seconds. And you have the minutes canceling out here. And so now we have seconds on the bottom. That's good. We need to convert revolutions to radian. Well, we can think about this in terms of rotations. It's 2 pi radian for 1 revolution. So revolutions will cancel now, and we have the units that we want. 2 pi radian on top, 60 seconds on the bottom, and we have some of these other numbers here that we have to multiply out. And once you multiply all of this out, you get 6 pi over 60 is equal to pi over theta. And I'm just going to finish solving this problem here. This is really pi over 10. Divide both the bottom and the top by 6. And multiply both sides by t, and you get theta is equal to pi over 10t. Theta equals pi over 10t. So then we can make this conversion by just saying f of theta, actually converting from f of theta to f of t now, f of t. Well, it's the same thing as what we had before, except instead of saying theta, we're going to substitute pi over 10 t. Theta equals pi over 10t plus 3/2 pi, and then the whole thing with 9 added onto it. And this effectively answers part A. Write an equation for h in terms of t. Well, we can just say that, f of t equals h. H is equal to all of that. And for part B, well, now it's not too difficult to do. 33 seconds after the wheel starts, how far above the ground is Emily? So all we really need to do here is substitute 33 into this problem and see what answer we get. Okay. So for the second part, part B, we're just doing f of 33, which is equal to 8 sine pi over 10 times 33 plus 3 pi over 2 plus 9. And this is going to be an approximate answer. And I'm going to use my TI-83 in order to get this problem done, just because I want to show you how to do these graphs as well. So it's more important that you understand the general problem, the general way to do this, not just how to solve one specific problem. Okay, so I'm going to wait for this thing here to fire up. There it is. Okay. And while we're waiting, you should think about a few things like, what if the wheel wasn't rotating counterclockwise? How would this change the problem? Or, what if Emily didn't start from the bottom, but she started from the side of the wheel? How would that change the problem? Okay. So I have my calculator up here, and I am going to graph this equation right here. 8 sine of pi over 10 t plus 3/2 pi plus 9. Okay. So you can go into your calculator, hit y equals, clear everything out there. 8 sine pi over 10t, so that's 0.1 pi t, or x in this case, because that's what the TI-84 gives me, plus 3 pi over 2, which is 1.5 pi, and then everything plus 9. And then, of course, the tricky business when it comes to graphing is always, well, what window do we use? Well, let's think back to our problem here. E is never going to be higher than 17. We already know that at the top of the wheel, she's never going to be higher than 17. She's never going to be lower than 1. So we'll give ourselves, and remember that x here represents t, and our original problem asks us to figure out where she is at 33 seconds. Okay? So I'm gonna go a little bit bigger than, and we will make sure you're in radian mode as well. My calculator has a reminder here for me. If yours doesn't, just hit mode and make sure that you are looking at radian mode here, and then you can hit opening here. It's taking its sweet time here, but that's okay. And one of the things that we can do to check is, just make sure our function lines up. So, for example, let's hit trace, at 0 seconds, she should be at 0 seconds. She should be at the bottom of the wheel. 0 seconds, she should be right here. So she should have a height of 1, which is true. And then, if she goes around 3 times every minute, so if she goes around like, after a minute, like 60 seconds might be too far, but if she goes around like 20 seconds, this says that she should return back to the bottom, which makes sense, okay? Because if she's going around the wheel 3 times a minute, she's going to hit the bottom, 3 times. Okay, so to solve our problem, I don't want to get too distracted here. We want to know f of 33, so we can just type in 33, hit enter, and there is your answer, that she should be right around 13.7 feet above the ground. Okay? And so I just want to go back to our problem here and just recap a little bit what we're doing here. What we're effectively saying is we have this problem with a wheel, with a circle, and it has to do with things moving around the circle. So we can connect that to our unit circle, and we build our function here, 8, 3 plus 3 pi over 2, and 9 here. We built this function by thinking about what transformations were needed to transform our unit circle into our Ferris wheel. And then we did some conversions here at the bottom to convert theta into time. Okay? And then we have our final function here. And from there you can answer just a lot of questions about where she's at after a certain amount of time, or how long will it take her to reach a certain point on the wheel. And again, I'm going to erase all this here and just put a few questions, which I call, food for thought here, for you to really think about, because, we can solve this one problem, but we want to be able to extend these ideas. So I'm going to call this, food for thought. Okay. And one of the questions I want to ask you and think about is, how does this function change? Okay. How does the function change? How does f of t change? Or we can also say f of theta change if, well, first, if Emily rotates clockwise. So what if she goes this way instead? Will that make a big difference? Okay. How would it change if, the Ferris wheel has a radius of, let's say, instead of 8 meters, what if it had a radius of 5 meters? What would that do to it? And finally, what if Emily starts at the left of the wheel? So instead of starting at the bottom here, what if she starts over here? Or better yet, a tougher question, what if she starts up here, where she isn't on one of the axes? And so that's something for you to think about. You should definitely ask your teacher about it if you can't quite figure out the solutions.